we see the agricultural technologies have evolved to a new paradigm. We saw Industry 4.0, so now we have Agriculture 4.0, and the traditional agriculture with the tractors and so on are completely surpassed by the new equipment and the precision they can provide in farm operations. So now in our presentation, we will speak about how this digitalization can optimize the crop production, so smart farming in a sense. So now I will present our patent. So the problem processing strategy of agricultural areas is very much dependent on the design of the field and also the experience of the driver of the tractor. With the very simple easy to understand problem, but the idea behind is to provide a method for simulating and determining an effective way of working agricultural area. So solve this problem with a simulation and data. So the solution, a simulation of an optimum drive track, which is function of the plant, the water or nutrient content, the ground, if it's a lot of humidity, nutrient contents, the dry mass of the soil, etc. The topography of the field, the crop, so the height, the presence of ditches, holes, obstacles, and also degree of maturity of plants. So a lot of different inputs. Very quickly, the use case. So we have a field to work, and we have a lot of data. We can gather the data thanks to sensors, for example, humidity sensors, temperature sensor. Sometimes we can see drones above the crops, etc. So we can gather a lot of information, these inputs. We put this information into a simulation is processing, and then we have output of the simulation, and this data are then incorporated into a machine. Here is the tractor, which is able to understand this data and to process. So we can have either an automatic control of the tractor or a manual, semi-automatic control of the tractor. So quite simple. Few words about enabling objects. It's about autonomous driving and optimal route calculation. We have a cyber physical system, so the computer system in which a mechanism or physical system is controlled or monitored by computer-based algorithm. This is the definition of cyber physical system. So in our case, the tractor is controlled by the software based on the simulation results. We have embedded systems and computational elements, and also IoT for network ability. So what does it mean in our case? We have a field. So the guy who drives the tractor does not necessarily optimize the trajectories. And then thanks to route length, tractor path, soil integrity, traveling time, consumption cost, and all this kind of inputs, we will optimize the processing and the exploitation of the field. And now we will discuss about an extension of this use case.
Okay, thank you, Matthew. Coming now from this description of the patent, we were thinking to expand this use case by creating a farmer community platform, and yeah, we would use this simulation method and all data we was producing thereby to feed a platform in order to manage resources, facilitate communication, and predict actions between other farmers and users of our platform. Thereby, in the first aspect, we was thinking to use the platform to facilitate the process to share over the platform machinery and tractors we are not using. So we could use process data to determine if machinery is not used, and offer it automatically on the platform, that other users get aware of it and could use it. And in this way, a platform user who would be interested could use this machineries, these tractors, however, and the platform would manage all the sharing process. And thereby we could even use GPS data to determine directly where is the position of a tractor or whatever, that the interaction of the proprietor is really less, you know. So to facilitate all this process of sharing equipment or tractors within an agriculture ecosystem. And now we will continue with facilitating communication.
Yeah, thank you. So facilitating communication, we have thought about a way to create a reflective framework to compare collective design method for forming system innovation. So how platform is somewhere also a possible place for direct persons to discuss to each other, so to have day-to-day chat. Here we have illustrated 3 examples of exchange possible. So you have this person who is talking about new fertilizer from Agrium based on nitrogen, and who has made the experience that it was great for her potatoes plantation. So she shares her best practice with the others. We can say users of the platform, but somewhere they are just peers in the agriculture activity. We have Tom who is there asking if there is somebody who's got experience in navigating forming drone. So that's true that for many newcomers in agriculture activity, it will be interesting to get advices from the one who have more experience in what they practice every day. And we have mentioned also Anna, who somewhere is thankful to another users, because thanks to the renting of the harvester, she could have used all the features and all the interest of the innovative function, and she somewhere very thankful for the way it has helped her, because when you are in such a sector, sometimes you are alone, and so getting an exchange with others, it's a way to solve exploitation problem, and to participate to a feedback loop all together. And so to let's say feed the experience database, use data to give automated answers when it's possible, but you have also the human face, and recommendation to the question. The human interface is a way also to get the administrator of the platform who is going to manage all the data, and to implement maybe how the knowledge can be shared on section to get specific section on precision agriculture, on new technology, ensuring quality control. And you can also have behind moderators who are there, just to manage how the talk are going. And now I'm going to let Natalia talk about another aspect of our farmer community platform.
Thank you, Aurélie. So to extend our use case even further, we were thinking on which problems can we potentially solve by having this community platform. And one of them was incompatibility of the neighboring cultures. As we see on this picture on the left side, it is called the companion planting chart, where you can check whether the particular plants are okay to be grown nearby together or not. Let's say we have two neighboring farmers, and they grown like totally different types of products, of plants. And for example, one of these plants require a specific fertilizer or specific watering system, which could be potentially harmful to the neighboring field. So in this way, by using our farmer community platform, the farmers could align on their practice on the plants they are growing, and in this way avoid this problem. It could be also useful for the newcomers because they could check which plants are being grown in the area where they come. And in this way, they could analyze what are the potential risks and opportunities for them on which culture to choose. Another aspect of this use case extension is also soil fertility. As we found out, it is beneficial for the ecosystem to have like increased biodiversity of the growing experience. For example, the farmer shouldn't be growing same type of culture like 10 years in a row. They should change from time to time. So we were assuming that potentially the farmers could also align on the sequence of these plants they are growing in their fields. Yes, to come into agreement on how do they manage this farming practice. So now we can move further to talk about the IP strategies.
So one question comes with digital transformation is how does this move the boundaries of the system? And from a product and development standpoint, we could say that the focus from to develop an equipment with physical limitation inherent to the tangible assets. I mean, if you want to optimize your tractor, you have engineering rules that you have to optimize. Means this tractor, if it is in location B, it cannot be at the same time in a location A. If the owner use it in A, another person cannot use it at the location B. So there is a move from optimizing this tangible asset to really developing dematerialized solutions, which are very much IP ecosystem, where there is an integration of many information from different environments. So we mentioned earlier the nature, the ground, the type of users, and all this is aimed to optimize the culture somehow, and the yield. And an important aspect, which is a big change also in this shift, is that it's this now new solution, this ecosystem is not tied to a specific brand of tractor, but it could be rolled out, implemented on any tractor or any brand of these assets. And this has, in fact, obviously implications also from an IP point of view on the generic IP strategy, where the value-added monopoly IP strategy is very efficient, somehow well-tuned to the former model, somehow where we are optimizing features on a tangible equipment. And it's very much, in this case, we are somehow creating exclusivity on physical differentiation features and USPs, while the hub monopoly somehow is more suited to protect, in fact, exclusive point in the digital ecosystem, where in this case we are much more, in fact, interacting between there are many more players involved in this field here. So one need to protect communication standard, format, interfaces to different equipment. We might also use, certainly we use GPS communication, for example. So it will need there is much more of a scheme of licensing, cross-licensing between these different partners, and people will try to influence somehow the industry standard here. So Rudina will present practically, which kind of IPR are suited to this extended use case.
Okay, so for the intellectual property rights, actually we can have patents. We can also have design, trademark, copyright, sui generis, right, and trade secrets. In digital smart farming, we could actually protect a lot of technologies. So we could have artificial intelligence-based optimization algorithms, such as technologies to help yield healthier crops, control pests, and monitor soil conditions. And along with this, actually, we could have protection for individual technologies employed in farming. So we can have some sensing technologies like sensors and smart machines used to measure and record farming processes. These sensors could be integrated into the farming equipment, for example, which can be used for checking conditions like temperature, humidity, carbon dioxide. Satellites could also be employed. So in addition, the sensing technologies can be coupled with acquired external data to complement direct observations. Data analytics solutions also for planting instructions, for example, yield models, and data analytics together with artificial intelligence or machine learning can help solve some complex farming challenges. So the use of data analytics helps farmers come up with important predictions, for example, like in crop harvesting time, risk of diseases, yield volume, for example. And data analytics tools help make farming more manageable and predictable. So we can also have like hardware and software systems. This include farming devices, equipment run by the respective software applications. And we can also have like telematics and positioning technologies. Telematics usually focus on tracking the GPS location of equipment. Telematics therefore can act as a security tool, for example. Then when GPS location tracking information is displayed on a visual map, teams can know where equipment and heavy machinery is located. So specifically, as telematics can not only record how the device is being used, but the data can be inputted into software solutions and applied to algorithms to determine how the equipment is performing. So as mentioned by my colleagues, communication systems. So to provide communication network connectivity, we have Internet of Things applications can also be used. Connectivity should be reliable enough to withstand like bad weather conditions and to ensure non-disruptive farming operations. For designs, we could have human-machine interface. So a digital instrumentation system can be developed to display, collect, store desirable tractor performance parameters. So we could see like a touch screen, for example, a user-friendly HMI assisted data unit displayed on tractor screens or webs. Then we can also have trademarks like OptiFarm, for example, to highlight that our technologies are optimized, which means they gives superior performance and benefits to farmers. Then we can have also copyrights. Software codes in farming applications and systems are copyrightable. Also the artificial intelligence database, including its architecture and framework. Then contents of artificial intelligence database can also be protected under sui generis right. And of course, we can also have trade secrets. This can include farm data, data which are protected for years, for example, by a farmer. So it should give a farmer an edge over other farmers as he would usually understand a particular field its conditions better than anyone else. So that's it for the intellectual property rights from our group.